morning, guys. Today we are doing SAS 4, and it is exploring higher degree polynomials. And it starts on page 125 in our workbook. So I'm going to go over this, and I'm going to go through the more practice with you as well. So this first question in our workbook says, focusing on distinct real zeros, which are indicated graphically as x-intercepts, find the maximum number of zeros that are possible for polynomials of each degree. So what I'm going to do first is I'm going to play around with this animation. So if you see, you have degree of 0. It's just boring straight line, okay? Boring straight line. Now, if I have a degree of 0, okay? If I move it up, it becomes positive, and if I move it negative, it goes below. So, if I just have a degree of 0, do I have x-intercepts? No, I don't. I don't have any. Now, if I move this back to 0, and now I look at a degree of 1. It shows us that I have only one distinct real 0. If I add in a second degree, it shows that I have 2 distinct zeros. If I add in a third degree, depending on how my graph sets and how I make it, I have up to 1, 2, and 3 degrees. If I make a fourth, let's go back here, shift it, maybe move it down a little bit. You notice that I have up to 1, 2, 3, and 4 zeros. So the pattern here for number 1, let me get to number 1. Is that for degree 0, I have a maximum number of 0 zeros. If I have a first degree polynomial, I just have 1. If I have a second degree polynomial, I can have a maximum of 2. So when I say maximum, that means that I can have up to the number 2. For third degree, I can have 3. Fourth degree, I can have up to 4. Fifth degree, I can have up to 5. And sixth degree, I can have up to 6. So what that means, and this is what we're going to talk about in number 2. So on number 2, if you look, it gives us from degrees 1 to 6. Okay? So what I want us to do first is on the right-hand side, I want you to write polynomial of odd degree can have any number from 1 to n distinct real zeros. Let me change the color so you can see it better. On the left side, I want you to write polynomial of an even degree can have any number from 0 to n distinct zeros. Okay, so these right here that we just wrote are two very important things to know for higher degree polynomials. Okay, so now I'm going to swap back to AgileMind. And we're given this chart. So we have to think. Let's do all of even degrees first. So remember, even degrees are 2nd degree, 4th degree, and 6th degree. So we just wrote that a polynomial of even degree can have any number from 0 to n distinct real roots. So what that means, if it's an even degree, we can start at 0. And we go to the number of zeros that our degree is. So if I have a 2nd degree, then I can have up to 2 distinct real zeros. If I have a 4th degree, I can have up to 4 distinct real zeros. If I have a 6th degree, I start at 0, and I'm going all the way to 6 degrees. Now, the only difference in odd degrees is that it starts with 1. So for 1st, 3rd, and 5th, rather than starting at 0, we are starting at 1 degree. So, in conclusion, if you have a 1st degree polynomial, you only can have 1 real zero. If you have a 2nd degree polynomial, you can have 0, but you can have 1, or you can have 2. If you have a 3rd degree, you can start with 1, or you can have 2, or you can have 3. If it's a 4th degree, that's even, so it don't have to have any. Or it can have 1, it can have 2, it can have 3, and it can have 4. 5th degree, it can have up to 1, 2, 3, 4, and 5. And if it's a 6th degree, it doesn't have to have any, but it can have all the way up to 6 real zeros. Okay? So, next, number 3. There it is, just showing you our chart again. Did I hit? Here, make sure. Let's go back and let's hit submit on this. All right, now I'm moving to page 4 on AgileMind. So it says, suppose you want a 6th degree polynomial with 6 distinct real zeros. Just construct a polynomial of 6 different linear factors. Here are 2 examples. So, when it's talking about the degree, it is talking about the number of x's that you have. So, in this first one, we have x, x plus 1, x minus 1, x plus 2, x minus 2, and x minus 3. So I am going to highlight my x's. So I have 1, 2, 3, 4, 5, and 6. So this is a 6-degree polynomial. And remember, yesterday we talked about setting our factors equal to 0 to find the actual zeros. So remember, everything in the parentheses, each set has to be set equal to 0 and solved for. In other words, guys, you can just change the sign, okay? So this first one is easy. We're just saying x equals 0. This one would be -1. This would be a +1. This would be a -2. This would be a +2. And this would be a +3. Okay? Same thing with the next one. All right, so now on number 3, it says construct a 6-degree polynomial with exactly 3 distinct real zeros. So we're going to make a few different ones. So the first one that I thought of, yours can be completely different than mine, or you can use mine. F of x equals x squared, x plus 1 squared, and x minus 2 squared. So now my x's, I have 1, 2. 1, 2, because I've got this 2 right here. 1, 2. So this is a 6-degree polynomial, but it asks us to only have exactly 3 distinct real zeros. So my zeros for this one is just 0 because I don't have nothing attached. Remember, you set your parentheses equal to 0, or you can just change the sign. So the second one would be a -1, and the third one would be a +2. Now, I want you to create 2 more on your own. All right, if you go to number 4, this is some reinforced pages. So, first it says, how many x-intercepts do the graphs of the following functions have? What are they? Justify your answer by a method other than graphing. Okay, so we don't want to graph it to look, but we want to factor it out. So first, x cubed. That's 1, 2, 3 x's. Then I just have this lonely x, so that's just 1. So remember yesterday when we factored something, we figured out what they had in common. So both sides have at least 1 x. So I'm factoring out an x. Remember, I want to get x cubed. And if I have an x, I need an x squared plus 1. So now we've got an x and a set of parentheses. So we want to do some solving. Okay, so remember the first one, I'm setting x equals 0. And I've got a 0. Get my x-intercept. Now, the next one's a little bit different. If I said x squared plus 1 equal to 0, first I'm subtracting 1. And I get x squared equals negative 1. Well, yesterday we talked about on the video that we cannot take the square root of a negative number. If we do, that gives us non-real imaginary zeros. So, this problem asks us, how many x-intercepts do the graph of the function have? Well, if it's imaginary and it's non-real, can you see it? No. So our answer here is x equals 0. We only have one x-intercept. These are non-real. All right. On B, we have a third degree polynomial because we have 1x and then here's 2 more over here because it's squared. So if we set those equal, we've got x plus 1 equals 0 and x minus 1 equals 0. If we solve, we're getting x equals a negative 1 and x equals a positive 1. So here we have 2 x-intercepts. All right, on the next one, it's also a third degree polynomial. And it says x cubed plus 27. So in order to solve that, we want to set that equal to 0. First, we're subtracting 27, and we get x cubed equals a negative 27. Now, just like when you have an x squared, you take the square root. When you have an x cubed, you take the cube root. So this is x equals negative 3. So here I just have one x-intercept. All right, now I want you to do or try D on your own. All right, if you go to page 127 on number 5, it tells us to construct a fourth degree polynomial with the following characteristics. So a fourth degree polynomial is going to have 4 x's. Okay, so first one's going to be the easiest one. Exactly 4 distinct zeros. So I am just going to do f of x equals x minus 1, x plus 1, x minus 2. My zeros would be, sorry, I messed my arrows up, boys. The boys talk about my arrows. 0, 1, negative 1, and 2. Yours can be completely different. I am just giving you the examples that I have used. Okay? Now, for B, it says we have exactly 3 distinct real zeros, but keep in mind, you have to have 4 x's. So one of those is going to need to be squared. F of x equals x plus 1, x minus 3, x plus 5 squared. So now I have 1x, 2x, 3x, but this 2 means I actually have 4. My zeros, remember we set them equal to 0 and we solve, or we can just simply change the sign. So a negative 1, a positive 3, and a negative 5. If it has exactly 2 distinct real zeros, x plus 2 squared, x minus 2 squared. There's 1, 2, 3, 4 x's. My zeros would be a negative 2 and a positive 2. Now, D, it says exactly 1. So, f of x, you're going to want to make your parentheses to the 4th power. X minus 2 to the 4th power. That means I have 1, 2, 3, 4 x's. But I only have 1 0, and that is a positive 2. Now for E, it says no real zeros. F of x equals x to the 4th plus 2. It has 4 zeros, but, or not 4 zeros, 4 4th degree polynomial, because it has 4 x's, but if you were to graph that, you would see it has no real zeros, so it does not cross the x-axis where you can actually see it, okay? Cannot actually see it. All right, number 6. It says construct a cubic polynomial with no real zeros. Okay, so you have to remember a cubic polynomial is a 3rd degree polynomial. At the beginning, we wrote what odd degree polynomials could have. Odd degree polynomials can only have, hold on, my pen cut off, can only have 1 to n real zeros. So we can have 1 real zero, it can have 2 real zeros, or it can have 3 real zeros. But since it's an odd degree polynomial, it starts with 1 rather than 0. So, number 6, construct a cubic polynomial with no real zeros. You simply just want to write that does not exist. And if you want to look back on number 2, you will see that when we had a 3rd degree polynomial, we only checked number 1, 2, and 3 for the numbers of distinct real zeros because it was an odd degree polynomial. All right, now I mentioned in class when you were here about a trick. Here's the trick. You want to know the trick. Otherwise, you are going to have to do so much more than what you need. Okay? So, what I want to do first is I want to fill in these blanks. And then we're going to draw each possible graph. Okay? So, first, if a polynomial has odd degree, the ends of the graph point in opposite directions. If the leading coefficient is positive, the left end of the graph points down and the right end of the graph points up. If the leading coefficient is negative, the left end of the graph points up and the right end of the graph points down. If a polynomial has even degree, the ends of the graph point in the same direction. If the leading coefficient is negative, both ends of the graph point down. If the leading coefficient is positive, both ends of the graph point up. Now, here is where you want to really pay attention today. All right. So this is on the same same thing. So we wrote odd, and then we wrote positive, negative, even, negative, and positive. Okay. First, I want you to draw a place like this. Up here, you're going to write odd and positive. Then you're going to write odd and negative, even, and positive, and even, and negative. Okay? So, for the first one, when the degree is odd and the leading coefficient is positive, it says the left end of the graph points down and the right end of the graph points up. So, I'm drawing me a graph. The left end points down and the right end points up. If it's odd and it's negative, the left end points up and the right end points down. If it is even, it goes in the same direction. So they either both point up or they both point down. So if it's even and positive, they both point up. If it's even and negative, they both point down. All right, this slide right here is the most important slide for today. Got it? Most important slide for today. All right, flip over. We're going to skip number 8. So you can mark out number 8. And go to number 9. All right. It's number 9 on your page 9 and number 9 in your workbook. So, first, on your paper, I want you to trace this scatter plot. All right. It asks you, what type of function might be appropriate model for this data? Okay. So we have something called an extreme value. Extreme values are maximum and minimum points. Here's a minimum, here's a maximum, and here's a minimum. Okay? When you look at max and min points, your degree is going to be one more than the number of extreme max or min values. So since I have 2 min and 1 max. I have a total of 3 extreme values. So 3 plus 1 is going to give me my degree. So this would be a 4th degree polynomial. Okay? We're going to practice the questions and you'll understand what I'm saying. All right. First, more practice question. Which statements appear to be true about the function graph? Select all that apply. Okay. It has 4 extreme values. Is that correct? Here's a max, here's a min, here's a max, here's a min. So yes, that is correct. It says it is concave down over 3 separate intervals. Well, it's concave down here, and it's concave down here. That only looks like 2. So that can't be right. Next, it says it's concave up on the approximate interval from -1 to positive, or to -1/2 to +1/2. That looks pretty accurate. Now, is it a 4th degree or a 5th degree? You have to remember that you had 4 extreme values. So in order to find the degree of the polynomial, we want to add 1 to that. So 4 plus 1 is not 4, but it is 5. So let's select our answers. It has 4 extreme. It is concave up, and it's a 5th degree polynomial. There we go. Okay, this one is extra tricky. This is where you got to read. Consider the function graphed here. Suppose that you were told that in addition to all of the behavior you see on the graph, the function has exactly 1 more local extreme value. A local minimum of y equals -40 and x equals -4. What might you conclude about this function? So, keywords here are in addition, and you have 1 more local extreme value. So here's 1, 2, 3, and 4. So on my graph, I have a total of 4. But it tells me, in addition, I have 1 more that sets at -4. So now I have 1, 2, 3, 4, 5 extreme values, and both ends are pointing up. So when both ends are the same and they are pointing up, it has to be positive coefficient, and it has to be an even degree. So our only choice here is a 6th degree polynomial with a positive leading coefficient. Okay? All right. So this one, I want you to do by yourself. In order to do this correctly, you will need to use number 7 in our workbook page. Okay? Number 7. If you use number 7, you should have no problem getting this one correct. All right, on this one, you're going to want to trace your scatter plot. And you're going to notice that both ends are pointing up and that you have 1, 2, 3 extreme values. So use what I've said. Extreme values, your degree is 1 more than the number of extreme values you have. So you do number 8. Number 12. We'll do number 12 together. The function graph is concave blank on the interval negative infinity to blank. So if it's negative infinity, we're going from here to here. So that will be concave down. Then it says it goes concave. Oh, that's wrong. I'm so sorry. Concave, that's not concave down. What is that? That's concave up because the end is pointing up. I'm so sorry. And then it goes on the interval from negative infinity to blank. And then it goes concave down from here to here on the interval blank to infinity. There's an inflection point at, well, my inflection point looks about right there. So remember yesterday, or maybe it was in class, I told you have to use your X point or your Y point when talking about your intervals. Your X. So if our inflection is 0, 2, then our intervals have to go from negative infinity to 0, pick back up at 0, and go to infinity. All right, number 13, you do on your own. You are finding the inflection point, and it will actually be where it crosses a specific spot, okay? Let me know if you have questions.